Okay, so now we're going to go ahead and start the flow simulation. You want to make sure and activate the flow simulation add-in through SOLIDWORKS. We'll have to give it a minute to boot up here. We'll have to remember in this simulation that we're draining the tank, so there's only one boundary condition, and that's where the water leaves the pipe down here. So we're assuming that the tank's already full. Okay. So you see this box that was created around the water tank, and that is called the computational domain over here. You can change the size of the box. And that has to do with the way that the flow is calculated. So next we're going to go up here to the wizard to begin our new project, our flow simulation. It's going to ask for some names. We're going to go to our unit system here, foot-pound second. And this part is important. It's an internal. We need to decide whether it's internal or external analysis. And I'm going to choose internal. And we need to check some boxes down here. If we don't check them, then the simulation won't do anything. So, at least I assume that. So, I'm going to choose the time-dependent gravity. That number looks right, negative 32.2 feet per second squared. Heat conduction in solids. This reference axis here is not, don't have to worry about that. Now we need to add our liquid, and it's just water. Everything looks alright. We need to choose our solid material for the tank, which I already determined beforehand was plain carbon steel. These are some extra choices. I'm just going to leave them as it is. I don't really care about heat transfer. Atmospheric pressure right there. We're going to click finish. So now our project is set up. We can view. Okay, so now we're at the point where we have created our model and we have started creating our flow simulation using the wizard tool. And this next step is very important. You will see that, you will see this little icon down here that says not watertight model. That means that, as you can see, the tank is open on that end and also down here at the pipe outlet here. So in order for us to do the flow simulation, we have to seal off both of those holes. That's just the way that it's set up. So we're going to click on this icon down here. We'll get this message. Fluid volume has failed because the model is not watertight. Do you want to open the Create Lids tool? Yes. So we want to create lids to cover these openings, which seems a little counterintuitive, but it's just the way that it works. So we're going to create a lid there. See that? every time we make a geometry change, it'll ask us to reset the computational domain. We want to click yes. Reset the mesh, yes, we want to do that as well. Okay, it's asking me to create another lid because I didn't seal off the pipe, exit outlet pipe down here. So I need to click on this face where I want the lid to be. Notice also that we want the lids have to be on the boundary between the fluid and the area that's outside of the fluid region, which I'll explain here more in a second. Okay, so now we're at the point where we want to discuss boundary conditions now that we've created our lids. So we want to go over here in the tree and insert a new boundary condition. Now at this point, we only have one boundary condition because we're just draining a tank that is already filled. So we want to select our outlet pipe, the lid that we just created. We have to select the inside surface of this lid. So that surface right there cannot be the outer surface. So we've selected that face. We want to specify simply as atmospheric pressure because it's a jet stream that'll be coming out of here. We're just going to give it that one condition. And this is, in fact, atmospheric pressure, 216 pounds per square foot. So we're going to click OK. So now we have our boundary condition there. And if you change the model view, we'll see that there is, in fact, the boundary condition that we just made. So, and you will see that in our project tree over here, environmental pressure. Next, we want to make some customized changes to the mesh that was already created. You'll see that the mesh is already, it's on automatic setup. We want to go into manual. You don't have to do this, but this is a good step since we have such a small, a big change in diameter right there. There's an option here for small solid feature refinement. We want to put that up a little bit. That determines how many the finer mesh that we have here at our outlet surface. Don't have to worry about curvature. We want to go to the cells themselves. We have level of refining fluid cells. We're going to turn that up to 4. At the fluid solid boundary, we'll turn that up as well. And I believe that's all we're going to do here. Click OK. Okay. So I have a project that was preloaded here on my project tree over here to determine the internal pressure in the tank. So I activated this project here, and I'm going to run it so that you can see what the run process looks like. I'm going to do a new calculation. Click on Run. You'll see that a solver window will pop up here. It's actually very, seems to be pretty involved. This all these computations. Depending on how many goals you put and what kind of goals you put, that determines how long the solving process will take. You can see here it's given us the total number of cells, fluid cells, salt cells. There was an invalid goal that I had here in this project, mass flow rate. Okay. Okay, so when the solver is finished, you'll see this window here with the little icon that says solver is finished. And we can see a bunch of different things. A couple of warnings, warning messages down here. It has to deal with our boundary conditions, so I made some mistakes with the boundary conditions, environmental pressure, and some of the goals that I made on this project. So, but it did complete the calculation. So I can go ahead and minimize that. And I can view the results down here. It's important to notice this unload and load button up here. That will load all the results from that the solver just did, or unload them. So that's kind of a key option there if you need to go back and make changes to your model or anything. So the results are loaded, as you can see here. So we can look at several things here. We can look at this mesh profile that I already named. Okay, so you can see that it made a mesh on this plane, this vertical plane here. You can see how fine the mesh is as well. You'll notice down here where the pipe is, some of the mesh is more fine, and that's because of some of the settings I did earlier with the customized mesh settings and refinement. You can actually play around with this a little bit, move the mesh and see how it changes along the inside of this water tank. Okay, so we can hide that, and let's look at the pressure profile, which is what I was interested in. So there is the pressure distribution, and as I said earlier, it seems that the highest pressure is down here in this red area, and it decreases. It increases linearly as you move down the holding tank. You can go to. So I decided to go ahead and look at another project that I had made earlier. This one increased tank height, where we should be able to look at the velocity profile inside the tank. Okay, so we have let's see, about 5 feet per second. That sounds much better. 4.5 feet per second. Okay, so we see the jet stream down here, which makes sense, coming out of the pipe whereas most of the rest of the tank is not moving at all. We can change this just to change it graphically, change our scale graphically. Maybe we can see it better, get a better visualization. So it looks like the maximum velocity in this case is about 4.5 feet per second coming out of the pipe. And what I did to get these various profiles down here was insert a cut plot that cut across this front plane right here so that we could get a visualization of what's going on in that slice of the tank. And you get a bunch of different options here for, in this case I did a contour velocity. Say OK. And that gives me the velocity profile that we just looked at. So this is a basic overview of flow simulation, and I hope you have enjoyed watching the video. Thank you.